Okay, hello everybody. Today we continue our discussion of linear operators and their properties. But before we go further, let me give some comments on the things which we have done last time. So first of all, last time we have discussed theorem 410, and I said that we will finalize the proof later, but actually we have already done everything and we don't need anything more to finalize the proof. Namely, what we have shown that for any positive epsilon, there exists natural number n such that for any x satisfying this condition, we have this inequality. Hence, this is exactly what we need. So from this, we get this. And this means that the norm of the difference between an and n is smaller than epsilon. That is, an converges to a in the norm, operator norm. That's all what we wanted. Hence, the proof is over. Okay, and one more remark. This is about lemma 412, I guess, or yes, 412. So yes, as it was noticed last time by one of the listeners, that actually here we don't need an open neighborhood, because what is written here, this means only that we have that this set is a neighborhood of 0, that is 0 is included with some open ball around it in this set. So actually our proof is totally sufficient to prove this equivalence. So I have added not necessarily open. So what we have shown that for any open set in X, we take any point in its image with respect to A, and then we have shown that even an open ball around this point is inside this image, and hence this image is an open set, and hence the mapping is open. So we have shown this. Okay, and yeah, and then the statement is nice and more convenient for applications, actually. Okay, so that's it. So now let us go to lecture number 9. Do you have any questions concerning these remarks? This and the previous one?
No.
No. Okay, so let us go further. So recall what we have done already. So we are going to discuss this theorem. It is one of important theorems concerning the properties of linear operators. So what we have known already. So we have given a definition of an open mapping. So a mapping between two metric spaces is called open if it maps open sets to open sets. And we have proved this criterion of openness for linear mappings. And now example. So consider the operator A, which maps L infinity. So let me recall that L infinity is the space of all sequences, such that supremum of over n, absolute value of xn is finite. Everything happens over k. What is k? Either C or R, as usual in this chapter. And also this set C0 is the set of all sequences which tend to 0. Again over k. And both spaces, both sets are Banach spaces with respect to the supremum norm and the supremum norm of a sequence xn. This is just exactly what is written here. Supremum over n, absolute value of coordinate xn. Okay, so we have these two spaces. We have a mapping A which acts as follows. And you see that if we have a bounded sequence, so a sequence which lies in L infinity, so satisfies this, then 1 over n times xn. So such sequence is, of course, a sequence which converges to 0. And hence, this is the element of this set. So now let us investigate this mapping. So first of all, yes, the mapping is linear. Hopefully it is obvious from the definition. But the mapping is not an open mapping. Why? Because if we consider the image of an open ball in L infinity under this mapping A, we obtain this set, and this set is not open here with respect to supremum norm. Yeah? So I recall that, let me call that P epsilon in C0 endowed with supremum norm with some, okay, for example, 0 with center 0 is the set of all elements Yn such that absolute value of Yn smaller than epsilon for any n. And actually, no matter how small the epsilon is, it should be fixed. And you see here, for any fixed epsilon, you can choose n such that this will be smaller, smaller, and smaller. So actually, this set does not contain an open ball with respect to supremum norm. And hence, the image of an open set is not open, and hence the mapping A is not an open mapping. Are there any questions? Okay, seemingly this is not the case, so let us go further. Remark 14, so let X and Y be two norm spaces, A be a linear and open mapping, then this mapping is surjective. That is, this is a mapping onto. And each element from here has a pre-image in X under this mapping A. How to prove it? Indeed, A of X, since A is a linear mapping, A of X is a linear subspace of Y. X is a linear space, A is a linear mapping, so A of X is a linear subspace of Y. But this linear subspace of Y contains an open ball. Yes, since it maps an open set into an open set, and hence this open set contains a ball, an open ball. Okay, this is also bilinearity of A, and hence, again, since this guy is a linear subspace, then if any so this guy is a subspace, is a subset of AX. So we take any element X from here, and then since this guy is a linear subspace, then any lambda X, or better to say alpha X, for any alpha from our K, again belongs to this space, and hence we obtain that. Was it clear? Was my explanation clear or not?
I think it's clear.
Okay. So let us go further. Theorem 415, so open mapping theorem, the theorem which we are interested in. So let X and Y be Banach spaces, so this is important. Let the mapping A be a linear operator, bounded or continuous, this is equivalent for linear operators. And let A be surjective, then A is open. So once again, in the general case, if the mapping is open, then it is surjective. In the case we have Banach spaces, and A is a continuous linear operator, then surjective implies open. So this is the theorem we are interested in before we prove it. So the proof is quite technical. So before we prove it, let us discuss why we like this theorem. Okay, so corollary 16, which has its own name, inverse mapping theorem or bounded inverse theorem. So let again X and Y be Banach spaces, A be bounded or equivalently continuous linear mapping between X and Y. And we assume that A is bijective. Then the inverse mapping is continuous. And hence this A is the so-called isomorphism in the category of topological vector spaces. That is, it is a homomorphism, the homeomorphism, that is A itself and its inverse, they both are continuous. So let us prove first this corollary. So we know that A is bijective. Hence, in particular, A is surjective. Hence, by this open mapping theorem, this A minus 1, sorry, first of all, A is open, and hence A minus 1 is continuous. So let us, we have discussed it somewhere. Yeah, so this was preliminary consideration that if, A minus 1 is continuous if and only if A is an open mapping. That's it. Do you have any questions? Okay, seemingly no. So let us go further. Corollary 17. Let X be a vector space which is a complete vector space with respect to two norms, such norm and such norm. And assume also that one norm majorates the other norm. That is, there exists a constancy such that for any element of our vector space, we have this inequality. Then the statement is that the norms are equivalent. So if X is a Banach space with respect to this guy and this guy, then so one-side inequality implies two-sided inequality. Okay, so let us prove it. So consider the mapping A, which maps X with a bigger norm to X with a smaller norm. And A map so has the following action. So acts as follows. So A of X is just X. So it's the identity mapping. Then A belongs to the space of continuous linear mappings from X to Y. So this is my X and this is my Y, so to say. Yeah. And the operator norm of A is just smaller or equal than C due to this inequality. Yeah, that's okay. Everything is clear?
Yes.
Okay. Since by our assumption, yeah. So this is the mapping. So it is injective. Hopefully it is clear that this mapping is injective. And also due to this inequality, this mapping is surjective. So this is a mapping onto, yeah, because each element from this space, that is element from X with finite norm, is also the element of this space, yeah, due to this inequality. So further, A is bijective. So is it clear that it is bijective, injective, and surjective?
Yeah, I think it's obvious.
Yes. Then we use this corollaries by corollary for 16. The inverse is continuous. That is bounded. So for linear operators, boundness and continuity is the same. That is for any x in x. Sorry, so I should write down something like that is there exists a constant c tilde positive such that for any x in x, this a minus 1 applied to x is smaller or equal than c tilde norm x, this norm in y. But this guy is just x. Yeah, due to the definition of A, you can guess how acts this operator. But what does it mean? This means that we have proved also this inequality, C tilde norm x, and hence the norms are equivalent. That's it. Are there any questions, comments? Okay, seemingly this is not the case. Let us go further. Corollary 18. Let x and y be Banach spaces again, A bounded linear mapping or continuous linear mapping. And let us assume that this mapping is injective, only injective. So the mapping, the inverse mapping. So since A is not bijective, the inverse mapping is not a mapping from y to x. But if we restrict A, so better to say, if we consider A not as a mapping from x to y, but a mapping from x to A of x, this is a subset of y, then this mapping is already not only injective but also surjective. And that's why it is bijective as this type of mapping. And hence, we may consider the inverse mapping as a mapping from this set to this set. Okay. That is, we may define the inverse as a mapping from here to here. So the statement is that this mapping is continuous if and only if the image of x under A is a closed subset in Y. So let us prove this corollary. So let us first show this direction. So so we assume that A of x be closed in Y. What does it mean? This means that if we consider this, so this is a linear subspace of Y, because A is a linear operator, A is a vector space, linear space, then A of x is again a linear space, and this is a subspace of Y. So if we consider this linear space and endow it with this norm of Y, we obtain again a Banach space. So once again, Y is a Banach space, that is a complete space. And this guy is a closed subspace, closed subset of a complete set, and hence it is complete itself. So it's a vector space which is complete with respect to this norm. So it is a Banach space. Now we are in the setting of corollary. Which one? I guess this one corollary. So by corollary for 16. A to the power minus 1 is continuous. We have just replaced y by this new Banach space, and now we have a bijective mapping between two Banach spaces. And hence, we have it. We have the statement. Now, opposite direction. So we assume that A is a linear and bounded or continuous operator from X and Y, that A is injective, and the inverse as a mapping from A of X to X, it is a continuous operator. So these are our assumptions. Let us show that A of X is closed. So let Yn be a Cauchy sequence. So we show that A of X is complete. So let Yn be a Cauchy sequence in A of X. Then using this property, we have that its pre-image is a Cauchy sequence in X. This is because A minus 1 applied to Yn minus Ym, norm in X, is smaller or equal than norm of A minus 1. This is something finite since A minus 1 is a continuous mapping, that is a bounded mapping, linear mapping, times norm Yn minus Ym in Y. So since this is a Cauchy sequence here, which is a subset of Y, then this is a Cauchy sequence in Y. So this tends to 0 when n and m tend to infinity. And this is something finite due to our assumption. Okay, so we see that the pre-image of this sequence is again a Cauchy sequence, but already in X. But X is a Banach space. Hence, there exists a limit. Since X is a Banach space. And again, then T of X just is the same as the limit of Yn in T of, sorry, not T, A. This is my A of X. So what we have shown that if we have a Cauchy sequence in this guy, then it converges and the limit lives in the same set. So the set is complete. And what does it mean? That it should be closed. Any complete subset of a complete set is closed. Okay, we have shown everything. Are there any questions?
It's clear.
Okay, perfect. Let us go further. So I have saved a lot of place. Okay. So let us go further and let us consider an example. So we have two spaces. Space of continuous functions with supremum norm and the space of continuous function with L1 norm. So let me recall that the norm L1 norm of x. Here it is integral from 0 to 1, absolute value of the function x of t, let's say, dt. Okay, so the mapping A is just the identity mapping from this space, normed space, to this normed space. The statement is that this A is a linear mapping, obviously. A is injective, surjective, and continuous. So A is injective because of this. Hopefully it is clear that A is injective. Concerning the statement that the mapping is surjective, so let me put it somewhere here. So this is, of course, smaller or equal than supremum over all t in the interval from 0 to 1 absolute value x of t times integral from 0 to 1 dt. But this is nothing else but the norm of x. So this norm, supremum norm of x. And hence, what do we see? So if we have an element of this space, that is the element, sorry, yes, what I wanted to say, surjective. So for any element from here, we have a preimage which lives here. Is it clear or not? Now it is not clear for me. Let me check if I have written everything proper in this example. Yes. Yes, so let me argue as follows. So what is my A? So norm of my A. So let me first write down like this. A norm of my A, this is a supremum over all x's whose supremum norm is small or equal to 1. And here we have norm of x's 1. And due to the estimate here, we have that this is smaller or equal to 1. So the mapping A is continuous. And then why it is surjective? Because why it is subjective? It's a good question. If we have element from here, it's a continuous function whose L1 norm is finite, what can we state? Do you have any ideas how to justify that the mapping is surjective? Okay, let us think about it. But nevertheless, so what we wanted to show, so this we will think about. The mapping is continuous because of this consideration. Yes, why it is surjective? Because we have a continuous function, and all continuous functions are integrable with respect, okay, Lebesgue integrable on a segment. Of course, if x is a continuous function, then absolute value of x is again a continuous function, and hence it is integrable. Okay? Agree?
Could you please repeat it again?
So I know, so we should know it from the mass theory, or I don't know, I guess it's a known fact that any f which belongs to C and then some segments, 0, 1, is okay, Riemann integrable and hence Lebesgue integrable. Again, absolute value of f is again a continuous function as a Riemann integral. And hence as a Lebesgue integral. Oops, integral. So now this guy is non-negative. So Riemann integrability implies Lebesgue integrability. And of course, when we speak about LP spaces, we always mean Lebesgue integration. But this somehow should be known, at least this should be known from analysis 1. And this is then the whole follows from the measure theory. And hence, we prove that the mapping is surjective. Okay.
I thought that if we want to prove the surjective, we need to prove the supreme of x is less than infinity.
Yes, but again, f is a continuous function, so it takes its so this is a compact set. So continuous functions attain their maximum and minimum on a compact set. That's it.
Yeah, I can understand why the supreme is less than infinity. I just mean that the proof of surjective is not prove the integrability. I mean if we want to show the surjective, we just need to say, okay, we for arbitrary x lives in C01 with norm L1.
Yes.
We have the property that f lives in C01 with the norm L infinity. That's all.
Oh yes, yes, I proved something else. Yes.
Okay.
Oops, 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 oops. So I have proved what? That this is okay, I have proved that this is a really sorry. I have proved again that this is a subset of this set, in a sense, yes? Yes, so if it is, no, stop. We consider this set with this norm. And this set with this norm. So what I wanted to say. So the continuity makes everything. This is what I wanted to say. So what do we have? We have that this guy is finite. So L1 norm of the function is finite. So let us make the exercise for all of us. Not now, but what we want to have. So f is a continuous function. And so integral of absolute value f of t dt is finite. Then, and this is what we are interested in, supremum of f of t is finite. But once again, since we have this, from this we obtain this stuff already without this extra assumption. Yeah, so if f is continuous on a segment, on a compact segment, then this supremum is finite. Okay. So yes, we don't need any words about integrability. Sorry. But I guess this is enough to justify that our mapping is surjective and injective. Injective because of this, surjective because each continuous function, even without this assumption, each continuous function has its maximum and minimum, attains its maximum and minimum on the segment. So we have this. Now we are satisfied. We all are satisfied or not?
I think now it's clear.
Yes. So about my integrability, it was something else. Okay. Yes. Okay. So we have shown that it is injective, surjective, and continuous. So bounded and hence continuous. Perfect. Now we want to show that the inverse mapping is not continuous. So how to show it? This is a standard counterexample. We consider, so we want to show this. We consider what we consider standard counterexample. So 0, 1 over n, 2 over n, somewhere 1. This is my t. And my function looks as follows. Yn. And here it attains the value n. So this is my Yn. Hence, what do we have? We have that the norm 1, L1 norm of Yn is equal to 1. This is the volume or area below the graph of the function, but supremum norm of this function tends to infinity. And this means that this mapping is not continuous. Agree?
Yes.
Okay, what does it mean in particular? This means that this set, so space of continuous functions endowed with the L1 norm, is not a Banach space. Because if it would be a Banach space, then this situation would be not possible due to corollary 16. We have Banach spaces, we have a bijective mapping, which is bounded, then the inverse is also continuous. If A is continuous, then the inverse is also continuous. Okay. And also this means that supremum norm and L1 norm are not equivalent. Because with respect to one norm, we have a complete space. With respect to another norm, this space is not complete. Hence, the norms cannot be equivalent. Questions? Okay, so this is like an example of how we can apply corollaries of open mapping theorem to show that some space is not a Banach space. Okay, let us go further. Example, okay, I have already written it. So example 20, let us consider another mapping from L infinity, which we have already discussed, to C0, which we have already discussed. And the mapping is as follows. So the same as in the example 4.13. So the mapping is linear. It is hopefully obvious from the definition. The mapping is continuous because in both cases we have supremum norm. So if we have a supremum norm of this guy is smaller or equal to 1, then the supremum norm of this guy is even smaller, and hence the norm of this mapping is smaller or equal to 1. Okay. The mapping is injective. Hopefully it is also clear from the formula that we cannot have different sequences which are mapped to the same element. Okay, the mapping is not surjective because, for example, this element, this is an element of the space C0, so it's a sequence which converges to 0, but it has no pre-image in L infinity with respect to this mapping, yeah, because the pre-image would be n times 1 over square root of n. And this is just square root of n. And this is, of course, not a bounded sequence. It does not belong to L infinity. And moreover, we know from example 4.13 that this mapping is not open. Not surjective, not open. Now, question. We would like to check if the set, so the image of L infinity under this mapping, so this is how it looks like. If the question is this set closed in our Banach space C0? So how to show it? So let me check. So yes, answer is no. And how to show it? We show that the inverse mapping is the mapping from here to L infinity, that this mapping is not continuous. So let us show it. But before we show it, so once again, what we have used corollary number, so this one. So the mapping, so we have two Banach spaces and the continuous mapping, continuous linear mapping, which is injective. So the inverse is continuous if and only if the image is closed. So now the image is not closed because we can show that this mapping is not continuous. So indeed, let us consider the sequence. So the element y, which is a sequence 1 over n. This is the element of this set, L infinity. And its pre-image is just the sequence of elements 1, 1, 1, etc. Nice element of L infinity. Consider the sequence. So consider sequence yn, which is defined as follows. This is 1, 1/2, etc., up to 1 over n, and then zeros. These are nice elements of course, again, A of L infinity. And again, we know that they are pre-images. They are just 1, 1, 1, and then zeros, zeros. So n times. What do we have then? So the distance between y and yn in the space C0, that is supremum norm, is equal to 1 over n plus 1. And this tends to 0 when n tends to infinity. So this is my y, this is my yn. The supremum of absolute values between differences of coordinates is attained at n plus 1th coordinate. Okay, so we have this. So we have a sequence, a convergence sequence. But if we consider pre-image, let me write down it nicer. So norm of pre-image of y n minus pre-image of y. Again, supremum norm everywhere. This is equal to 1 for all n, because this is the pre-image of y, and this is the pre-image of yn. So you see, supremum norm of the difference is just 1. This shows that a minus 1 is not sequentially continuous and hence is not continuous, because in metric spaces, sequential continuity and continuity are equivalent. It was corollary for 18. This A of L infinity is not closed. In C0. Questions, comments? Okay, so we have two examples which show how we use the open mapping theorem and corollaries from this theorem to show, for example, that some set is not a closed set. So we answer such type of questions. And in the previous example, we showed that some space is not a Banach space and the norms are not equivalent. Again, using the open mapping theorem and corollaries from this theorem. Okay, so now it's a good time to prove the theorem, open mapping theorem. So this is a statement once again. We have two Banach spaces, and A is a linear and continuous mapping, which is surjective, then it is open. So I'm not going to present you the complete proof because there are some technical steps which are long and they're not too much from functional analysis. It's just, okay, technical things. Nevertheless, so what we want to show? We show that there exists R and rho positive such that an open unit, an open ball around 0 in Y with radius rho is a subset of the image of an open ball around 0 with radius R in X. So if we show that this holds, we may apply lemma 212 to claim that the mapping A is an open mapping. So we call me this lemma 212. Yes, so if we have this, then we have this. Okay, so first step, which is technical, lemma. So if we have a Banach space X and a norm space Y and the mapping A, which is linear and continuous, then for any R and rho, this statement implies this statement. So here we have the closure of this image, and here we have just the image. So this is a purely technical stuff, so it is omitted in the lecture, but Well, I have used the book of Werner on functional analysis, but this is in German. But now we have a lot of tools how to translate. So you're welcome to look at this book as well and use some translation tools. Okay, so this lemma will simplify our approach. Namely, now using this lemma, it is enough to show that there exists R and rho strictly positive, such that an open ball around 0 in Y with radius rho is a subset of the closure of the image of open ball around 0 in X. So then these two lemmas make the business. Okay, so this is what we want to show. And in order to show this, we use Baire category theorem. So this is an important theorem. We have skipped the theory of metric spaces, hoping that it is somehow known for you from analysis course. Just in case it is not known for you, this is the statement of Baire category theorem. So let XD be a complete metric space. Assume that we can represent X as a countable union. So countable is important. Countable union of some sets which are closed. Then the statement is that there exists at least one element around, among all of them, so among all Xn, such that this element contains an open ball with strictly positive radius. This means that, roughly speaking, that we cannot represent a complete metric space as a countable union of nowhere dense sets. At least one set should be not of this type, so not nowhere dense, and hence this means that there should be at least one set which contains an open ball. Okay, so this is an important statement which when one studies theory of metric spaces, this statement is wow, it's an important statement. Looks very abstract, but actually it is used in many proofs of many important theorems, in particular also here. So we are going to use this theorem. Okay, once again, this is what we want to show. So let us show it. And these are our assumptions. So these are our assumptions. Okay, so let me open my notes. Okay, so A is a surjective mapping. So first of all, we of course can represent X as a union of open balls, countable union of open balls. So this is true. And since A is surjective, hence we can represent all Y as a union of A of open balls. That is so such union exhausts all X, and such union exhausts all Y due to surjectivity. And now if we increase these sets by making the complete closure, by making the closure of these sets, so this is not a smaller set than this one, so we again obtain Y. Okay, everything is clear?
Yes.
Perfect. So since Y is complete, we use the Baire category theorem. So it is a complete, so it's a Banach space, and hence it is a complete metric space. And it is represented as a union, countable union of sets which are closed. Then there exists at least one N such that this closed set, the corresponding closed set, is not nowhere dense. That is, it contains an inner point. What does it mean? This means that there exists a ball around this point, which so that the whole ball lives in this closed set. So this is exactly the step where we use this Baire category theorem. And we have this countable union of closed sets. Okay. So what we want to show further. So we have this. What do we want? We want a ball around zero, not around some y, but around zero. So this is the next step. So we have this. Now we show this. This is again a technical step, but let us show it. Okay. So let z be some element of this open ball in y around zero. Then we may consider y plus and minus z. So you see this is an open ball around zero. This is a set which is symmetric. So if z belongs to this set, then minus z also belongs to this set. And hence, shifted by y, both points, plus and minus z, they belong to the open ball with radius rho around y. But we know that this set is a subset, so we have already shown it, is a subset of this closure. But it may happen that these 2 points belong to the closure of this set, but not to this set itself. Yeah, so probably such points do not have pre-image with respect to A, pre-image inside this open unit ball. So big attention, yeah. But since it is the closure of this set, so it contains only the points of this set and limit points of this set. Hence, we can approximate so better to say the following. So for any natural number k, there exist points xk with sign plus and minus, so 2 points, which are elements of our open ball in X around zero, such that norm of A of X plus or minus K minus this point Y plus minus Z is smaller than 1 over K. So once again, these points, they live in this closure, but probably not in this image of the open ball. So probably these points do not have pre-images with respect to A, living in this ball. But nevertheless, we can approximate these points by points like this. So the points from here. And this is how we did it. Okay? Everything is clear here?
I think it's better now. Stop 10 seconds.
Okay. So probably let me summarize once again. We have 2 points, which live in the closure of this set. Hence, these 2 points can be approximated by a sequence of points living in this set. Because the closure of a set contains either the elements of this set or the limit points of this set. So they are limit points of a sequence of points here without the closure. And this is how we have constructed such points. Okay, so let us go further. I hope this step is clear, more or less. So since my open ball in X around 0 is convex, with a convex set and symmetric, together with points xk plus and xk minus, also such points minus xk minus. Yeah, due to symmetry, if this guy lives in my open ball around 0, then minus this point also lives in my open ball. And also such convex linear combination, 1/2 xk plus minus xk minus belong to this open ball where Bnx0. So this is a convex linear combination of this guy and this guy. Agree?
Yes.
Okay. So consider xk, which is exactly this convex linear combination, xk plus minus xk minus. It is the element here. And then what do we have? A of xk minus z, the norm in y. It is, so A is a linear mapping. xk has this formula. So we write it down. It looks as follows. Norm 1/2 here A of xk plus minus the point y plus z, one bracket extra, minus 1/2, and here A of xk minus, and here be careful, y minus z. Norm is closed. So what has happened? So I have added this point and subtracted this point. And I also have inserted this point and used the linearity of A. So I have this. And then there should be minus 1/2 of this with plus, and also this guy, minus z. And this minus z compensates this plus here, so now we have minus. Yeah, so be careful here once again. Here we have plus, here we have minus. It is so because of this minus z, extra minus z. Now we use the triangle inequality for the norm. It is smaller, smaller or equal than. Okay, let me still try to write down here. So now I use these inequalities for any point. For both points. So this is via this inequality and via this 1/2 is smaller than and equal to 1 over 2k. And again, the second norm, again using this inequality, is again smaller or equal than 1/2 times 1 over k. Everything is 1 over k. So what we have shown? We have shown that this point z belongs. So what we have shown, so before I write down. So we take any point z from this unit, so this open ball around 0. And we have shown that for any k, there exists such that this holds, this inequality holds. What does it mean? This means that we take any arbitrary element of this unit, of this open ball, and we, with any so with arbitrary preciseness, we can approximate this point by images of elements of this ball. Hence, this means that Z belongs to the closure of A, B, X, and 0. But this is exactly what we wanted to show. Yeah, so we want to show this. And we have done it. Okay, so this step is shown. Oops. So this step is shown. And now we use lemma 421 that we can even skip this bar. So even without bar, this is true. And then we use lemma 412 that from such statement follows that the mapping is open. Okay, done. So please pay attention that we used, so a substantial element of the proof is the bare category theorem. Okay, let us go further, or you are welcome to ask questions or make comments.
Excuse me. Actually, when I learned this open mapping theorem, maybe there exists another proof that does not need to use the bare category theorem, because as I remember, in my school they only use the bare category. They didn't mention the bare category theorem and prove this open mapping theorem.
Well, actually, there will be the next theorem, closed graph theorem. And another way to prove open mapping theorem is to prove closed graph theorem first, and from this get open mapping theorem. So, but we will discuss the relation between two theorems in the sequel. So either you start with open mapping theorem and you prove closed graph theorem, or vice versa. But the first theorem which you prove, you have to prove with bare category theorem.
Okay, sense.
At least as far as I know. Okay. So let us go further. Yes, closed graph theorem. So it's like another section. So the previous section was devoted to open mapping theorem, and this is an important theorem, and hopefully you have an impression. What is it? Now closed graph theorem. Before we start this, the formulation of the theorem, again, some motivation. So before we considered bounded or continuous linear operators, and sometimes they're too good for being useful. Namely, in the context of evolution equations of this form, I mean, we consider U is a mapping from like some time segment into some Banach space X. Banach space. Then if this mapping is nice, continuous, and even differentiable, we can consider this stuff, and it will be again a mapping from time interval to Banach space X. And hence, the right-hand side should be also, for each t, it should be the element of X. Hence, A should be the mapping of, from X to, A should be the mapping from X to X. In order to make, to make sense to this equality. So, but if we are interested in evolution equations where operators A are linear differential operators, for example, Laplacian, or more general situation, general just different linear differential operator, we cannot assume that A as a mapping from X to X is a bounded linear operator for some Banach space of functions. Why? Because what does a differential operator? So if we start with some smooth function, then after application of such a differential operator, we obtain a function which is less smooth. And this less smooth function should be also the element of the same space X, because the left-hand side is the element of space X. And hence, if our space X contains not sufficiently smooth functions, then we cannot we cannot actually define the Laplacian or some differential operator on the whole space. So there are some troubles with considering such operators, differential operators, as bounded linear operators on the same Banach space, you see? Okay, that motivates the definition of a closed operator. So it's an operator which is not necessarily bound or continuous, but still sufficiently good and really needed for the applications. So let X and Y be two normed spaces, D be a subspace of X, and A is defined not on the whole space X, but only on its subspace D. So and A is a linear operator. Again, thinking about Laplacian, and let's say X and Y like L2 space everywhere, then you cannot define Laplacian reasonably for all L2 functions. They should be reasonably smooth. Okay, so we define the graph of the operator L. It is the set of such couples where X belongs to the domain of definition of the operator L, and A of X is the image of the point X. And these couples, so this set, is a subset of this Cartesian product. So if the operator is not defined on the whole space, it is reasonable to specify its domain of definition concretely, so that we know what is it. So that's why when we are not considering only bounded operators, so the domain of definition is not obvious from the context, we always consider a couple, the operator and its domain of definition, or just domain. So the couple AD is called a closed operator as a mapping from X to Y, or D to Y. If its graph is a closed subset of this set, it is a direct sum. I recall that we have discussed it. So if we have a Cartesian product of two normed spaces, then we can organize a norm here, which converts this set to a normed space, which is defined, which gives us the direct sum of two spaces. And the norm is just, so norm in this space is just sum of the norm in X plus norm in Y. Yeah, so to say coordinate-wise norm. Okay. Remark, so if A is the linear operator, then its graph is a linear subspace of this space, norm space. I hope it is obvious. Next remark, so we have introduced the notion of closed operator before we have discussed open mappings. So there is nothing to do. So there is nothing common between closed operator and open operator. So there are no relations, reasonable relations between them. So better to be, instead of saying closed operator, to say a graph closed operator, but classical notation, classical notion is, so this guy is called closed operator. So in applications, taking into account, for example, Laplacian in L2, so D is often a dense subset space of X. So the operator L, considered as a mapping from X to Y, is defined not everywhere in X, but on some subspace, often a dense subspace of X. Once again, A is a Laplacian, this is L2, and A is defined on the space on a subset of Sobolev functions. Okay, well, sufficiently smooth functions. Okay, lemma, criterion of closeness. So let X and Y be norm spaces, D be a subspace of X, and A is a linear operator defined only on D. The operator A is the couple A and D, is closed if and only if the following holds. So for any sequence of elements in D, such that the sequence converges somewhere in X, and such that the image of the sequence under A also converges somewhere in Y, it follows that this limit actually also element of D, and this guy is nothing else but the image of this X under A. So what is written here means that this set, so the graph, is just sequentially closed in this space. And in metric spaces, closeness and sequential closeness, it is the same. That is, we can deal only with sequences. Yeah, so operator is called closed if its graph is a closed subset. So what is written here, this is the sequential closeness of this set. Okay, so what I want to stress here, so this is actually not about operator, but mainly about D. Yeah, so if we take D smaller, then we may lose the closeness of operator. That's why it's a very important question in applications when one considers equations, semi-groups, what is the domain of definition of our operator? Because we really need a closed operator, so we really need a proper domain of definition to which guarantees that the graph is closed, the subset, that the operator is closed. Okay. Remark, if we have a bounded linear operator, or equivalently a continuous linear operator, then it is closed. And yes, it is defined on the whole space X. So the domain of definition is just the whole space X. Indeed, what does mean that A is bounded linear operator or continuous linear operator? Continuous means sequentially continuous because we are in the setting of norm space, they are metric spaces, so continuity and sequential continuity, it is equivalent. So A is continuous, hence sequentially continuous, hence for each sequence in X which converges to X in X, A of Xn converges to A of X. And hence you can compare with this criterion of closeness. From continuity we have this, and this is stronger than this. Is everything clear?
Excuse me. So you mean that there might exist some operator such that it's closed, but it's not continuous.
Yes, there are. We will consider a simplest example a little bit later. Yes. So now we have extended the setting. So not only, so before we had only operators which are defined on the whole space X, and they were bounded or continuous. Linear operators. Now we define operators on a subspace. And sometimes it is not possible to extend the operator to a bounded linear operator on the whole X. But still, such operators are useful for applications. Again, thinking about Laplacian. Okay, in the space L2, the space here and here. Yeah, in order to apply differential operators, the functions, the elements of our space should be sufficiently smooth. Okay. So we have extended the notion of operator so that they are defined. Well, you see, once again, in our previous formulations, we often considered this situation. We didn't speak about necessarily Banach spaces, but norm spaces. So we may be in the situation then, so D is a subspace of X, so it is a norm space itself. Yeah, so we may consider A as an operator from norm space D with norm X into norm space Y with norm Y and consider linear operators. So this is one point of view, but as I said, for applications, it is often more convenient to consider another point of view. We have spaces, good spaces, and then we consider an operator which is defined on a subspace, probably dense subspace of above given spaces. And in this situation, if D is not the whole X, we cannot speak about bounded operators. Yeah, we cannot define it, but we may define the notion of a closed operator. The relation between closed operators and bounded operators, for example, so a given, we will study it right now. So what the first remark is that if we have a bounded linear operator that is continuous linear operator, this means that the operator is defined on the whole X, that is domain of definition is the whole X, and this operator is closed. So this is the first observation. And this is the justification. So let us go further. Example, yeah. So as X and Y, we consider the space of continuous functions with supremum norm. As D, the set of C1 functions. And as the mapping A, I consider differential operator of the first derivative. So F is mapped onto its first derivative. So this is D. It's a dense subspace here with respect to supremum norm. And this is my operator. Obviously, A is a linear operator. A is not continuous. So what do we have? How to prove that F is not operator A is not continuous. So let us consider Fn of t or Xn. Let me make X here and here. Consider Xn of t, which is equal to t to the power n. Then A Xn of t is just n t to the power n minus 1. And hence, what do we have? We have that the norm of Xn, supremum norm, is just 1. But supremum norm of X, so Axn is n. And hence, what do we conclude? There exists no positive constant C such that norm of Ax is smaller or equal than C times norm of X for any X. in D. Of course, such xn, they are, of course, elements of D. They are C1 functions. Everything is fine. So you see, roughly speaking, of course, we could consider A as a mapping from normed space D to the normed space Y. But the problem is that this operator is not bounded. And this means that if we only stop with our previous considerations, we are not able to discuss such operators as a mapping from a normed space D to a normed space Y. So sometimes, so there exist unbounded operators, which are still important. That's why we introduce another class, closed operators, and taking into account the motivation of evolution equations. We are usually in the situation when x is equal to y and it is some big Banach space, and A is defined on some norms. A is defined on some subspace of a big space, and sometimes in important situations, this subspace is dense in the big space X. Okay, so once again, this important operator, it is not a bounded operator as a mapping from normed space to normed space, but it is a closed operator as an operator from X to Y with this domain of definition. How to motivate this? So let xn belong to D. That is this space of smooth functions with the statement with the property that xn converges to some x in this supremum norm in X, and its derivatives, so their derivatives converge to some element, let me call it Y. Again, convergence is in supremum norm, and everything happens in Y, which is the same space as X. Then, and this is what is known from analysis, of course, we are not going to prove it, but we know that. What does this mean? This means that we have a sequence of functions which converge uniform to a function. Then it is, of course, again, a continuous function. And here the same, we have a sequence of continuous functions which converge uniformly on a segment to a function. Hence, this is a continuous function. And it is shown in the course of analysis that this function is just the derivative of this function. So hence, x also smooth, and its derivative is just y. That is, a of x is equal to y. This is a course of analysis. We don't prove it, but this is a known result. But this means exactly that the criteria of closeness is satisfied. That is, the graph of this operator A is a sequentially closed set in this space. Okay.
So, although we said the closed property is weaker than continuous,
Yes.
but when we consider closed, we assume something in advance. For example, we will assume Y already lives in this space.
No, once again, let us see the definition. A is the operator from D to Y, linear operator. Probably it is an unbounded operator as an operator between two normed spaces. But we may consider its graph and we say that the operator is closed if its graph is a closed subspace of this direct sum. So it's a weaker notion than the notion of bounded linear operator. So any bounded operator is closed, but in general, not all closed operators are bounded. Differential operators is exactly the case. But of course, it is supposed to have some theorems which says that in good cases, closed operator means bounded. And this is exactly what is done here. But we have to go to the theorem. So let us try yes, so exercise. Let us just skip it because we have no time. So I want to formulate closed graph theorem. So I skip something. I skip it and examples as well. And I want to make the following. So first of all, remark, so if we have two Banach spaces and a subspace in the first Banach space X, so if we have a mapping, which is a closed operator, but is not bounded operator as a mapping from this norm space to this norm space, no, I should say in a more accurate way. So as we have just seen, this example with this first derivative, so a differential operator, it is defined on a subspace of X, and it is a closed operator, but it is not a bounded operator as a mapping from X to Y. Recall that last time we have discussed another situation when we have an operator A, which is defined on a, for example, on a dense subspace of X. And if A is a bounded operator as an operator from D to Y, then it can be extended to a bounded operator from X to Y. This was, let me find this theorem. Yes, I guess this theorem. So if we have a norm space, let D be a dense subspace. If A is a bounded operator as a mapping from D to Y, it can be extended to a bounded operator from X to Y with the same norm. Now, what is the situation here? Assume D is a dense subspace of X, and A is a closed operator. Sometimes, as we have seen in the example of first derivative, we cannot, so A is not a bounded operator as a mapping from D to Y, and hence we cannot extend it to bounded operator as a mapping from X to Y. That is, its domain of definition is really smaller than X. Even if it is dense in X, we cannot extend A to a bounded operator on the whole space X. But if occasionally we have an operator from a Banach space to Banach space, which is closed, so Banach space, it is important. That is, we may assume that the domain of definition is the whole space, Banach space. Then actually from this follows that A is a bounded operator. And this is what is done in this theorem, closed graph theorem. So let X and Y be Banach spaces. This is important because in the definition of closed operator, we only considered norm spaces. But now they are Banach. If we have Banach spaces and A is a linear operator which is defined on the whole Banach space, then the following statements are equivalent. A is continuous, equivalently bounded. A is a closed operator, and then its graph is a closed linear subspace of this direct sum. Okay, so actually I expected that we prove everything today, but seemingly this is not the case. So probably, so what should we do? I guess we should stop here and continue next time. And you have some time to think about the differences between bounded operators and unbounded but still sufficiently good, namely closed operators.
Okay.
Okay. Are there any questions so far? Okay, so I have skipped a few slides. We will discuss them hopefully next time. I mean, all what was previously. Okay.